Let me continue with the fourth rule. Yeah, the fourth rule, we call this the mapping rule. There are three elements of the mapping rule, and the third one is actually a rule that we have seen before, namely the bijection rule, but that's okay. This is just a repetition of that one. This is called a mapping rule because basically we are dealing with a mapping here, a function. The first one, if you can find a function f, which is a mapping from sets A to B, and this is a surjective. You must already know right now what is a surjection. Yeah, this function is surjective. Then the number of elements inside of A must be more or equal to the number of elements inside of B. Second one, if you can find a function, any function from A to B, and this function is injective, then the number of elements in A must be less or equal to the number of elements in B. And the third one, if this function is both surjective and at the same time injective, then this function must also be a bijective one. If the function is bijective, then the number of elements inside of B must be equal to the number of elements inside of A. Yeah, so this is basically just a function. If you can create a function, if you can find a function from these two sets, then look at the characteristic of this function. If it is surjective, then you know this particular rule, and if it is injective, then you know that the number of elements in A must be less or equal to the number of elements in B. Okay, now out of this rule, there is a particular rule that is really, really important for us. Give me a couple of minutes. Okay, let's continue. From this rule, we can create another rule, and this rule is really important. It's a very powerful rule. Look at the second rule here. Yeah, look at the second one. The second one says that if you can find a function f from A to B that is injective, then the number of elements in A must be less or equal to the number of elements in B if it is injective. Now, let's take the contraposition of this implication. Let's take the contraposition. The contraposition is basically says that if not this one, then not this one. This is a contraposition. Yeah, that means that if it is not true that the size of A is less or equal to the size of B, what does it mean? Well, it means that if the size of A is larger than the size of B, then this function can never be injective. This is the contraposition. Yeah, so this is the contraposition. So if the cardinality of A is larger than the cardinality of B, then this function from A to B, any function whatsoever from A to B, can never be injective. And this is called the pigeon principle. What is the pigeon principle? The pigeon principle basically says, look at this, if the cardinality of A is larger than the cardinality of B, then any function from A to B must map at least two elements of A, yeah, to an element of B. So that it basically says that if this is the case, then there must be at least one occurrence. That must be at least one occurrence in which you take two elements of this one and map these two to an element in B. Yeah, and this is actually really logical because the size of this is larger than this one. Of course, there must be at least two elements of this one that you map to one element of this one. It can be even larger. There may be also three elements of this one that you map to one of this one, but at least two elements of this one is mapped to one element of B. Yeah. So why do we call this the pigeonhole principle? Well, if you have a set of pigeon, and if a pigeon flies to a particular pigeonhole, and then you have more pigeons compared to the pigeonhole. So what happens there? Well, what happens is that when you look at these pigeonhole, you must find at least one pigeonhole that contains two pigeons. Yeah, that's why we call this a pigeonhole principle. So the pigeonhole principle is basically the contraposition of the second rule in rule number 4. How do we use this? What is the use of this rule? Yeah, what is the use of this rule? Well, the use of this rule is actually has something to do with the beginning of our lecture today, but I will return to that. Okay, let me first generalize this pigeonhole principle by rule number 6, the generalized pigeonhole principle. If, look at this, if the cardinality of A is larger than k times the cardinality of B, k times. So for example, if the cardinality of A is equal to 100 and cardinality of B is equal to, I don't know, 25, then this is basically 4. I'm almost 4 times, yeah? 4 times the cardinality of another one. Then any function f, any function at all, that maps from A to B must map at least k plus 1 elements of A, k plus 1 distinct or different element of A to an element of B. This is easy. This is basically a straightforward generalization of the pigeonhole principle. In this one, the k is equal to 1. If it is equal to 1, then you map 2 elements to one element. If it is equal to k, then you map basically k plus 1 elements to an element of B. Okay. So, what is the example? Well, an example is, well, our previous example. Listen to this. This is the previous example that I show you basically in the first slide. Let me return to the slide, to the previous slide. In our first slide here, we have 90 numbers. There are 90 numbers there. Yeah, there are 90 numbers. And each one of these numbers can be up to, I don't know, I don't remember, 20 or 25 digits. So let's return. Now we are going to show you the proof of the claim that I made in the beginning. So assume A is the set of all subsets. So this is basically the power set, the set of all subsets of these 90 numbers. The set of all subsets. Think about that, the set of all subsets. Because we have 90 numbers, then how many subsets do we have? Well, the number of subsets do we have will be 2 to the power of 90. Okay? Now, that's the second one. Each of that number is of 25 digits. Look at this, 25 digits. So each of the numbers there, each of that 90 numbers is of 25 digits long. Yeah? That means that if you just add them together, these 90 numbers, just add them together. So add the first one to the second one and so forth until the 90th one, then their sums, the overall sum cannot be larger than 90 times 10 to the power of 25. Okay? Now, this is A. The second one is B. Well, B is the set of numbers from 0 until 90 multiplied by 10 to the power of 25. How many numbers are there? This is easy. This is just basically numbers from 0, 1, 2, 3, 4, 5, 100, 1 million, and so forth. And the last one is basically 90 multiplied by 10 to the power of 25, which is the sum of all these 90 numbers. Now I'm going to create a function, that maps elements from A to B, from A to B. So this is a B. This is the B, basically all of the integers from 0 to 90 multiplied by 10 to the power of 25, and A is the subset, yeah, the set of all subsets of these 90 numbers. Okay, now how many subsets are there? Well, if you have n elements, then the number of subsets that are possible out of these n elements is 2 to the power of n. So that means that the number of elements of A is equal to 2 to the power of 90. 2 to the power of 90 is a little bit larger than 1.237 multiplied by 10 to the power of 27. Okay, now what about B? B, the cardinality of B is 90 multiplied by 10 to the power of 25 plus 1. What is this 1? 1 is because there is 0. We start from 0. 0, 1, 2, 3, and so forth until the last one is 90 multiplied by 10 to the power of 25. And this is a little bit smaller than 0.901. Look at this. There is no, there's supposed to be not 1 here. And if you look at this actually, this is an over approximation, because we basically take 90 to the multiplied by 10 to the power of 25. But if you look at the individual numbers, the individual number is smaller than that. They are not equal to 10 to the power of 25 each, every one of them. So this is smaller than 0.901 multiplied by 10 to the power of 27. This is larger. So so that means that the number of elements in A, or the cardinality of A, is larger than the cardinality of B. How many larger? Well, 1 times. This is around 1 times. This is 1 times larger than this one. It's not twice or three times, but then 1 time. A is a little bit larger than B. So based on the pigeonhole principle, then this function that we just create, this function f, maps at least 2 distinct elements from A to B. What does it mean? This is basically what I mean by the claim. The claim says there must be at least 2 subsets, 2 different subsets of those 90 numbers that when you add them together, produce the same number, exactly the same number. So that means that there must be at least 2 subsets, 2 distinct subsets that have the same sums. So you see, what I have just done here is basically a proof without showing you, exactly those 2 elements. So my argument is an abstract argument. We still believe this proof, but this proof is not constructive. A constructive proof basically tells you what are these 2 subsets. I didn't do that. Yeah, I didn't do that. But still, if what I just want is just to prove this claim, this is actually enough. Okay. Okay, let me continue. So then we're going to see the 7th rules. The 7th rule is called the generalized product rule. Remember again about the product rule. The product rule basically says that if you have the product of several sets, then the number of the cardinality of the product will be the product or the multiplication of the cardinality. Yeah. So, but there is some catch there that you have to remember. Namely, you must be able to produce the sets first, you must know in advance what are the elements of each set. Let me return again to that rule. This is the product rule. A1, A2, and so on until AN. There are different sets. Well, they can be also the same sets, but it's okay. But what does it mean? It means that you must really know what are the elements of A1. If you know that, then this rule basically applies. If you know the set, if you know the elements of this set, then this rule applies. But sometimes you may encounter a problem in which you don't actually really know the elements of these sets, but you know how to create them. You don't know the individual element, but you know how to create them. In this case, you are going to use the generalized product rule. The generalized product rule says something like this. Pay attention. Yeah. Let S be the set that contains sequences of length k. So the sequence is of length k. If there is n1 possibility for the first term, n2 possibility for the second term, n3 possibility for the third term, and so forth, then the cardinality of S is equal to n1 multiplied by n2 multiplied by n3 and so on until nk. This is what we call the generalized product rule. You may say something like, well, what is the difference between this from the previous one? So the ability to see the difference is basically important. Yeah. So in this one, you know S, you know the resulting sequence. You know the resulting sequence. Yeah. So if what you know is the resulting sequence, but you don't know how to create them, then you proceed by using this one. But if you do not know, if you don't really remember, if you don't really care about the resulting sequence, but you know the individual ingredient, the individual components, then you use the normal product rule. Yeah? Okay. So let me show you an example of this one. And you will be able to see, I mean, try to look at the difference between this one and the normal product rule. Will you be able to use the normal product rule to solve this particular problem? So look at this the next example. This is three pawn on the chessboard, and three pawn on the chessboard. So the question is, how many ways are there to position three pawn on the chessboard such that each one of them are positioned in a different row and different columns. In a different row and different columns. So you have three pawns, yeah, and now you have these three. Well, you does not have to be three pawns. I mean, anyone, any. I mean, three kings is also is okay. Yeah, so you just basically take three pieces, and then you position these three pieces. Now the only rule is that you have to position these three pieces in such a way that they know two of them are in the same rows or in the same columns. So if you think about this, it's not actually easy to imagine how to solve this one. Yeah. And if I ask you, what is the first element? What is the first set, the second set, and the third set? You will not be able to answer that. But actually, you can go right away to the end. You can look at the sequence. Yeah. So you bring this problem to the problem of sequence. So this is the sequence. Look at this. This is the sequence. I will create a sequence right now. I will create a bijection from the configuration of these three pawns to a set that contains these sequences. And the sequence has this particular form. What is the sequence? Look at this. The first one here, B1, is basically the row in which you place the first pawn. This is the column in which you place the first pawn, and so forth. So this is the first pawn, the second pawn, or the third piece. Yeah, so B1, B2, and B3 are basically the rows, the different rows, and K1, K2, and K3 are the different columns. Okay, now you can imagine right away the elements of this set. But if I ask you, how do we create this sequence out of the individual set, we will have problem to answer that. We cannot imagine that. But we know how to create this set. Yeah? So, and of course, there is a rule also. The rule says that they cannot be at the same column, at the same rows. So how do we enforce this rule? Well, you can imagine that. Yeah? In order that the rows and the columns of each of these pieces are different from each other, then you take the first one. Yeah? So take the first piece. When you are positioning this first piece, you have basically complete freedom. You can position it anywhere you like. You can put it in any row you like, in any column you like. So what does it mean? For the first piece, you have 8 possible rows and 8 possible columns. Yeah, but once you position this piece and you are positioning the second piece right now, then your possibility is reduced by 1, because you can no longer put this piece on the same column as the first one, or on the first row as the previous one. You see, there is only 7 possibilities right now for B2. And similarly with B3. In the B3, in the third piece also, yeah, there is only 6 possibilities left, because you cannot use the row that's already been occupied by the first piece and the second piece. You see the idea? So the idea then, there are 8 possibilities for B1, 7 possibilities for B2, 6 possibility for B3, and the same case also applies for K1, K2, and K3. What does it mean then? Then you know there are how many possibilities for this one? 8 possibilities. For this one also 8 possibilities. For this one 7 possibilities, 7 possibilities, 6 possibilities, 6 possibilities. Now, according to this generalized product rule, if you find a sequence of k elements, and there are these possibilities of the first one, these possibilities of the second one, these possibilities of the third one, until these possibilities for the kth one, so you just have to multiply them all together. So this means that 8 multiplied by 8 multiplied by 7 multiplied by 7 multiplied by 6 multiplied by 6. So this is the configuration. This is the possible configurations. 8 multiplied by 6 multiplied by 7 multiplied by 6 to the power of 2. So you see? So this is how many ways for us to position these pieces on the chessboard. Okay. So let me continue with the next rule, and then after this rule, we take a break, a couple of minutes. So the next rule is called the permutation rules, and then but what is a permutation? Let's see first. A permutation of a set S is a sequence that exactly contains every element of S exactly once. Yeah? So this is basically, if you have a set how do you convert this set to a sequence? You can call this by permutation. This is an example. Assume let S be a set that contains A, B, and C. These are all permutation of S. It is actually a mistake here. The mistake. This is actually no longer a set. So we cannot use a curly bracket. This must be. This is supposed to be a normal bracket or an angular bracket. So this is not a set anymore. Yeah, this is a sequence. What I mean is that this is a sequence. This is also another sequence, another sequence. So you have to change it a little bit. This is no longer a set. So the first sequence is ABC. The second one is ACB because they are basically sequence. That means that they are different sequence. So the position is actually determines that they are a different sequence. BAC, BCA, CAB, and CBA. These are all possible permutations of S. So you know permutation already. Okay? Now, if we have a set S and this set is of size n, so the cardinality of S is equal to n, how many permutations are there for S? I think you have already encountered this even in high school. Yeah? So we can actually use, if you think about this, you can actually use the generalized product rule for that one. So how do we compute the number of sequence? The number of sequence, the number of permutation. The number of permutation. How do we compute them? So a number of permutation is like this. If you think about this, this is if you position this one, yeah. So I take any element for this one and I position it in the first one. So how many elements are there that I put here, that I can put here? Well, there are three possibilities. There are three possibilities here. Well, what about this one? Well, because I have already taken one element here, so there are no longer three possibilities here. There are only two possibilities. So there are two possibilities here. What about this one? There is only one possibility. So that means that three possibilities, two possibilities, one possibilities. What? How many permutations are there then? So this will be 3 multiplied by 2 multiplied by 1. So this is easy. So this basically is equal to the generalized. Yeah. So there are n possibilities for the first element, n minus 1 possibilities for the second element, and so on until there are two possibilities for the n minus 1 element and one element for the nth element. One possibilities for the nth element. So that means that based on the generalized product rule, the number of permutation that we have is n multiplied by n minus 1 multiplied by n minus 2 and so on until multiplied by 2 multiplied by 1, and this 1 is equal to n factorial. So Pn is the number of permutation of a set that contains n element is equal to n factorial. Okay, so this is a permutation. So the last rule that we have seen is the generalized product rule, and out of this generalized product rule, we know right now the number of possible permutations. If you have a set that contains n element, then the number of possible permutation of the set of the elements of this set is equal to n factorial. Okay. So let's continue. The next rule is called the division rule. Assume that we have a function f, and this function is called k to 1 if this function maps exactly k element from the domain to one element on the codomain. Yeah. So if this function maps k element from this left hand side, yeah, from the domain to one element on the codomain, then we call this function k to 1. K to 1. Okay, now we have this division rule, rule number 8. If you have a function f that's mapping from A to B, and this function is k to 1, yeah, so you know this k to 1, then the number of element in A must be equal to k times number of element is in B. This looks like trivial also. This looks like this is really simple. But how to use this is actually not really straightforward. Yeah. So if you have a function and this function is k to 1, then the number of elements in the domain A is equal to k times the number of elements in the codomain. Yeah. So let me show you a couple of examples. One example. How many ways are there to sit n nights on a round table? Yeah. So you have n nights. So and then they assume that you have also a round table. Then how many possible ways are there to sit them, to sit these n nights on the round table? There's a catch. Look at this. If two configurations are considered the same, if they are just a rotation of the other configuration. So one configuration is considered the same as another configuration if one is just a rotation of the other configuration. What does it mean by a rotation? A rotation means that, well, if you just rotate them, assume, for example, you have a round table. A round table is just a circle. And if you consider the first round table, the first night is on the north side, for example, on the north side. And the second one is the one on his left hand side, and then this left hand side, and so on and so on and so on and so on. Yeah. But you see, we can also consider that the first night is actually not on the north side but on the south side. So this is just a rotation. If you just rotate them and they are the same, then they are considered as the same configuration. Yeah. So how many nights are there? How many ways uh, are there for us to sit them? How do we answer this? Well, assume that A is the set of all permutation of these nights, and B is the set of all configurations, all different seats configuration. We can map every permutation that exists in A to one configuration in B by placing the first night on the permutation on his seat. The second the second night in the permutation on his left hand side, and so on. And you can imagine that. So take any permutation in A, the permutation of the nights, take any one of them, take the first night first, put it anywhere you like on the round table, and then take the second night, put it on his left hand side, take the third night, put it on the left hand side again, and so on and so on and so on. Yeah. So, but then this mapping is actually n to 1. Why is it n to 1? Because you can actually just rotate them. So, like I said before, take the first night and put it anywhere you like on the round table. So you may put it on the north table, on the northmost table, for example, or you can put it on the southmost table. You can put it anywhere on this n table, basically. Sorry, n chair, yeah. So and seat. So put it in any seat. How many seats are there? There are n seats. So that must be then an n to 1 function. So this mapping is basically an n to 1 function from A to B, because by performing n cyclic rotation of this sequence, you have basically one configuration. So you you just rotate them n seats. This is just one configuration. So according to the diffusion rule, then the number of configuration, the number of possible configurations there is equal to the elements of A, the elements of, sorry, the elements of B, the number of elements in B, or the cardinality of B. The cardinality of B is equal to the cardinality of A divided by N. Because what? Because the function is an n-to-1 function. If this is the n-to-1 function according to this theorem, then the cardinality of A is equal to K multiplied by the cardinality of B. So what is being asked from us is the cardinality of B. So that means n factorial divided by n. What is n factorial divided by n is equal to n minus 1 factorial. So you see how to use this division rule.